What about now? Can you see things or not?
Yes,
sir. Screen is visible.
yes, sir.
Yeah. Okay. So shall I start? Yeah. So good afternoon all. Sorry, good evening all. Yeah. So as the anchor was telling, first of all, thanks to Surjit sir for calling me and giving me this occasion. Okay. Today I'll be talking about a specific random forest based algorithm called GPU-RF screen. So this is mainly used for virtual screening for the faster execution of drug discovery. Yeah, so our title is Application of Machine Learning Algorithms for Computational Drug Discovery. If time permits, I'll be also describing one of the other technique called self-organizing map. So two techniques I'll be having. One is supervised learning based, other one is unsupervised learning based. Okay. Yeah, you can see the outline of the agenda of the talk today here. First of all, I'll introduce AI, then introduction to drug discovery, computer-aided drug discovery, then virtual screening in drug discovery. This is a particular task which will fasten the drug discovery process with the help of computation. Yeah. Later, I'll be switching to machine learning based algorithms for virtual screening. First one is random forest based, which one is a supervised algorithm. And self-organizing map based technique is an unsupervised algorithm. Yeah, the results and publication also I'll be showing you. Yeah, I'll start with a remark from our Alan Turing, the great scientist. Yeah, he told like this: we can only see a short distance ahead, but we can see plenty there that needs to be done. So his computability test, Turing computability test, was very famous. Yeah, so I'll just define what is AI. Yeah, AI is termed as new electricity. So we all know that electricity has once transformed various industries, and now equally AI is revolutionizing all these industries like healthcare, transportation, etc. Yeah. So the main goal of AI is to make computers more useful by letting them take over dangerous or tedious tasks from human being. Yeah. So I just wanted to disclose this with a group of passionate students, researchers, PhD students, and faculty members. We have formed a technical club at NIT Calicut, the name of which is AI Club. So today I have one more other team member here. His name is Prathimesh. He is from AI Club. He'll also be talking in between. Yeah. So my total 2 hour, I am dividing into 3 sessions. The first one I'll discuss about machine learning techniques. Then Prathimesh will introduce deep learning techniques, the basics of CNN and object detectors. And third session will be handled by me. There I'll be introducing you a novel object detector called efficient-centered it. Yeah, so the definition of artificial intelligence: it is a science and engineering of making intelligent machines, especially intelligent computer programs, said by John McCarthy. So the other definition is AI is a study of how to make computers do things at moment people are better. It's said by Rich and Knight. When you see the history of AI, these are the main milestones. So McCulloch and Pitts in 1943, they introduced neural networks which can learn. Okay, and Minsky in 1951 he built a neural network computer, and in 1956 Dartmouth conference, these 4 eminent people, McCarthy, Minsky, Newell, Simon, they met each other, and the topic named artificial intelligence was coined. The name of the topic.
Are you moving slides? I'm just moving a slides. We just see the first screen.
Oh, you're only seeing the first screen?
Yeah, I could see like that. I'm not sure of other people.
Okay, then actually I'm moving. I'm in the fourth or fifth slide.
I just felt so, you are just, you might be telling of the other slides, but I see just the first slide, application on machine learning by Dr. Jayarajan.
Yeah, this is Surjit, right? Hello?
No, this is not Surjit.
Yeah. So Surjit, can you just respond? I'm changing slides.
Yeah, it's okay now. It's okay.
It's moving?
Yeah, now it's moving. We could see the birthplace of artificial intelligence, 1956.
Yeah, just see that. Just tell me whether it is moving now.
I'll do so. Now it's on the birthplace of artificial intelligence.
But I am in other slide now. History of AI.
On the seventh floor.
Yeah, history of AI. I am in other slide called named history of AI.
Yeah, I could see,
Sir, can you share us the entire window like that, entire screen? Then I think it should be okay.
Entire window. One second. Can you see now?
yeah, history of
Slides are
AI.
changing.
Yeah, now it's working
Yes,
well.
sir. Tell me.
Yeah. Okay. Thank you. Thanks for informing me. Okay.
Okay.
Yeah.
No?
So I was talking
Sir,
about the
slide
history
is
of
not
AI.
changing.
Yeah. I can continue, right, Surajit? Still,
Yes. Now it's changing, sir. Now it's
can you
changing.
see history of AI?
Yeah, we could see
Yes,
history of
yes.
AI.
Now it's changing. Now it's off.
Yeah. Okay, I'll continue. Okay. So in Dartmouth,
Okay,
in
sir.
Dartmouth conference in 1956, this four eminent people, McCarthy, Minsky, Newell, and Simon, they met each other, and the new topic named AI, artificial intelligence, was coined. Okay. 1952 to 1969, this time McCarthy introduced in exactly in 1958, he introduced Lisp programming language. Then 1957, the perceptron was introduced by Frank Rosenblatt. Then 1965, MLP, multi-level perceptron, was introduced. 1986, again neural network came for a second wave. Yeah, so this time a famous algorithm called backpropagation was introduced. In 1989, convolutional neural networks were found, and 1991, recurrent neural networks (RNN), the idea of RNN was introduced. In 1997, LSTM, the extended form of RNN, which is a long short-term memory, was introduced. In 2007, when you see the GPUs were introduced, GPUs basically they were for graphical execution. But then, so due to the fabrication capability of the GPUs, so with a framework called CUDA, so we can execute parallel programs over there. So in 2012, Adam Optimizer was introduced, and 2014, Ian Goodfellow invented GAN network, generative adversarial network. Then in 1916, Pascal GPUs were introduced, because from 2007 to 2016, GPU witnessed different fabrication changes from Fermi to Kepler to Maxwell to Pascal to Turing to Volta. Now we are in Ampere, and the latest one is Hopper architecture. Yeah. So the advantage of Pascal architecture is it supports unified memory. So both the CPU and GPU, they can share the common memory. Yeah. So the NVIDIA has a page migration engine using which page fault can be easily faced. Okay. So in 2017, the architecture, transformer architecture, which is an extension of LSTM, was introduced. Yeah. So as I told you, 1956, AI was the name. The topic AI was found at birthplace of AI at Dartmouth workshop. So the four people, John McCarthy, Marvin Minsky, Alan Newell, and Herbert Simon, they met each other and they gave a proposal. Okay, so the areas of AI and some dependencies. So when you see, it has many subtopics, but machine learning, which is termed as a modern AI, the modern AI, it is called as a modern AI. So I'll be more talking about machine learning. Okay, so as a case study, so I'm taking a drug discovery application, the name of which is called virtual screening. Yeah, as you can see here, so it's actually a search space reduction from a larger space, 10 raised to 6 to 10 raised to 7. The virtual screening is reducing this into 10 raised to 2. Introduction to drug discovery. Yeah. So I told you virtual screening is a part of drug discovery. So drug discovery is an inventive process of developing a new drug which will be therapeutically active to a disease-causing target molecule. So the main terminology we will be seeing here are target and ligand. In fact, drug discovery deals with the design of a molecule that is complementary in charge and shape to the target to which it binds. So when you see the traditional drug discovery pipeline, it requires a lot of wet lab experiments with the target and large number of molecules. So large exploration space, actually we have a larger exploration space which will require longer execution time and money. So that's why the computational drug discovery, computer-aided drug discovery is famous now, which breaks this bottleneck by using modern computational techniques. So you can see a computer here with the help of modern computational techniques namely data mining, machine learning, artificial intelligence, and graph matching. Yeah, so we can solve this. So the term virtual screening. Yeah, virtual screening is a computational technique used in drug discovery for evaluating large number of molecules to identify lead molecules that can be optimized to give drug candidates. Yeah, it's nothing but it's a search space reduction from an initial from the scratch, from a larger space. We are finding some lead molecules which will be then given to the wet lab, using which they will be actually inventing the new drugs. Okay, so kind of screening. Okay, so because of the virtual screening, so the drug discovery consider enormous chemical space of 10 raised to 60. So in fact, we have in combinatorial chemistry, so we have 10 raised to 60 compounds. So this virtual screening, which is a kind of simulation, can take all these components. So this will really speed up the drug discovery process while reducing the need for expensive wet lab work. Yeah, the virtual screening, there are different kinds of virtual screening. We can categorize this into ligand-based method and structure-based method. In structure-based method, we have some technique called docking, which uses the structure of both the ligand and protein. And using key lock method, they will identify the new drugs. Whereas in ligand-based drug discovery, we are only using the details of the ligands, the small molecule, which they are binding to the structure of the protein, are only will be available. And the details of these, utilizing these details of these small molecule, we will be creating a model using which the activity of the new molecule can be easily found, whether it is active or inactive. So we have similarity searching, pharmacophore mapping, and another method is machine learning based method. We are only looking into machine learning based ligand based drug discovery. Okay, the issues in virtual screening, I told you earlier that our input is large. So since the spectrum of input for virtual screening is too large, serial computing will not be much of helpful. Yeah, so the task of training the model using millions of molecules can take too much time. Also, the screening billions of molecules will be an awful task with serial computing. So that's why we need parallel computing. In this the work, I'll be showing you a GPU-based machine learning based ligand-based drug discovery process. Yeah, in fact, we did this work by collaborating with an open source drug discovery consortium of CSIR, which was locating at IISc campus in 2015. Yeah, so the GPU accelerated ML-based virtual screening techniques. You can see here the larger search space we will reduce down into 10 raised to 2. So 10 raised to 12 will be reducing down into 10 raised to 2. So for this, we are using first of all machine learning and GPU accelerated machine learning techniques we are applied here. So first method. Yeah. So as I told you, we are in this method. I'll be showing you random forest, which is a supervised learning algorithm. So this is the problem description. Given information about the reaction of a set of molecules to a target, predict the reaction of new molecules when they interact with the same target as either active or inactive. Yeah. So we all know that random forest is a supervised learning algorithm. It's a committee of weak learners for solving the prediction problem. So random forest is an ensembled model in which decision tree CART is used as a weak learner. CART stands for classification and regression tree. So CART follows greedy top-down binary recursive partitioning that divides the feature space into set of disjoint rectangular regions. In fact, they are dividing and partitioning the input feature space. Yeah, each internal node has an associated splitting predicate, which can be seen here. So in this binary decision tree, you can see the leaf nodes here, and this yellow nodes there. We have by using splitting predicates, split function. You can see the split function here. By applying split functions, the feature space will be further subdivided into further nodes. Yeah, so random forest. As I told you, the forest comprised of many decision trees. So typical random forest algorithm you can see here. So the main input parameters are capital N, number of training samples, small n, number of decision tree in the forest, number of trees in the forest, and capital M, total number of features, and small m, number of features splitting a node. The algorithm works like this. Yeah, we set a number of trees, n number of trees, okay, by taking m features, okay. So by using bagging and bootstrapping, we create n training samples for each tree, and we grow the trees. And in each node, the splitting can be done by m of capital M random features. Yeah, we split the node on the by using the feature by using m features that best separates the training samples in the node with regard to their output value. For each instance in the finally, yeah, after training, yeah, for inferencing, yeah, for each instance in the test sample, yeah, we will pass it through to all the trees in the forest. Yeah, so all the separate trees will be giving the result, from which the majority of the result will be taken out. So the final output of ensemble is the majority vote. Okay, that's about random forest. Now coming back to the data, yeah. So drug discovery deals with molecules, compounds, right? Yeah. So we can view molecule as a vector. Yeah. For this particular experimentation, we have taken the details from NCBI PubChem. So we have received the data in the form of SDF file, structured data file. Yeah. So this structured data file is a graphic representation. So here, by applying a pre-processing with the help of PowerMV, so we are separating the features from it. 179 descriptors are separated from this. Now a molecule can be viewed as a set of descriptors, 179 descriptors. Finally, a molecule can be considered as a point in a multidimensional descriptor space, like 179 space. Yeah, so you can see the example here. So compound 1, yeah, there are various features you can see here. Yeah, for only the viewing purpose, 1, 2, 3, 4, 5, 6, 7, 8 features are only seen. The last one is a label, either active or inactive. Yeah, for this purpose, we have taken the target as Mycobacterium tuberculosis, TB. Yeah, so the different features are, you can see molecular weight, blood brain barrier, pH value, etc. Yeah, now you can see the actual model. So the random forest classifier for this particular versus training purpose. So the training set, right? So the features are extracted by using PowerMV. So this utilizing these details, we are training the random forest. Forest comprised of many trees. So once it is trained, yeah, to this model or unknown data, the test set which doesn't have this label value will be given, and one by one this will be giving the result, whether active or inactive. Yeah, the main issues we are facing here is model creation and prediction serially for millions of molecules takes too much of time to complete the virtual screening process. That's why we thought of parallelizing the same algorithm, the serial algorithm which we derived here. We were not using any third-party algorithm. So the serial algorithm we derived here, we thought of parallelizing it. Yeah. So now I will tell you a technique that we applied in the tree formation. Yeah. So to grow a decision tree on GPU, a hybrid method is developed. Okay. The hybrid method uses combination of depth first and breadth first constructions. So the breadth first tree construction is utilized at tree top, whereas once we reach to a certain level, the tree construction will be switched to the breadth first level, but the breadth first tree construction after a threshold will be followed. Yeah, this crossover threshold can be set by a number of nodes grown in the tree. Yeah. So the proposed parallel training algorithm you can see here. So the random forest creation, which is shown here. So as I told you, using bootstrapping, the training sets was identified. Then both the DFS and BFS. So till certain level, the DFS is applied. The depth first technique is applied for growing the tree. After a certain threshold, the breadth first techniques are applied in parallel. Okay. So when you see in depth first, so the predicate splitting is done with the help of Gini index algorithm. Gini index feature details. Yeah, so you can see that yeah, these things will be done parallelly here. Similarly, BFS parallel implementing a BFS setup is easy. So yeah, because BFS will have many lanes, so each of these parallel lanes can be built parallelly. Yeah. So once the training is done, the prediction also can we can apply easily parallelization for prediction also. So I told you forest comprised of many trees. Okay. So yeah, so the elements from our test set, we will be passing through all the trees in the forest. So that's why we can do this execution parallelly. For each tree in M, we can run this parallelly, evaluate the features M on the tree, and finally measure by using majority voting system. We can finally classify, means declare the label of the unknown compound. Okay. Yeah, so the data set used for this experimentation, for any of the machine learning algorithm, the details of the data set is very important. You can see here. So as I told you, the bioassay SDF files were taken from NCBI PubChem repository. So the feature extraction tool used was PowerMB. So we chosen 179 descriptors. So you can see AID datasets, AID 1332 in AID names. You can see the many the samples here. So the first sample comprised of only 1193 molecules, and the last one AID 2314 contained 296,456 compounds with this bioassay. Yeah, so as I told you, we implemented both the serial and parallel version. But when you see the performance, recall, precision, F-score, and accuracy, yeah, I think we got almost the same. So which is proving that parallelization is not affecting the performance. Then the speed up we achieved is for training we achieved the speed up. When you see here, almost 10x speed up is achieved. For smaller data sets, the speed up is less due to the overhead in the CPU GPU data transfer. For larger data set, there is a visible computational boost of tenfold. Similarly, in prediction, you can see the speed up of 5 to 60 times achieved. Yeah, for the classification, the test set was taken from GDB17, which is treated as a chemical universe data set for unknown compounds. Yeah. So as I told you, we published this work in a Springer Journal of Cheminformatics. Yeah. The name of this tool is GPU-RF screen. Yeah, so I'll also show you one more case study in the same journal. GPU-based self-organizing maps for versus screening. Yeah, here we are using an unsupervised technique called self-organizing map, which was introduced by Professor Kohanen. Yeah, so it's a type of artificial neural network ANN to produce a low-dimensional discrete representation of the input space of the training samples. It's basically a 2D palette. It is implemented as an unsupervised system of competitive learners. So this makes the SOM useful for visualizing low-dimensional views of high-dimensional data. So I told you 179 descriptors. When you reduce down into a 2D map, so you can see many similar compounds appearing in the same box. Okay. So the working of the SOM you can see here. The input, comprising of x vectors, each of length n, and finally we will be getting an output, which is basically the cluster n, which contains basically m clusters, y1, y2 up to ym. Each of the p vectors in the training data set is classified as falling in one of m clusters. Yeah, so this is our core idea. You can see that we are utilizing two SOMs here, self-organizing maps, one for active set and another for inactive set. Yeah, the moment when you are downloading the data set from the PubChem repository, in fact, we are getting in two folders. One is inactive set, other one is active set. So I told you this is an unsupervised algorithm. So utilizing these details, one map is trained. You can see the inactive map, other one is active map. Yeah, now these two maps are trained. So when we have these unknown compounds for screening. So we'll be one by one, we will be giving to these maps. So certain scores will be developed, and you're utilizing these scores, and we have came up with an equation using which this novelty detection is found, and by utilizing which the classification can be done: active, inactive, and one more classification, unclassified. Yeah, so this is the beauty of this. So the chemical compounds which come outside the line of this particular property. So we are classifying it as unclassified. Yeah. So you can see the algorithm here. So this is a serial algorithm in which the training of active and inactive maps are done, and finally model is created. Okay, so in which the novelty detection is easily found by applying this, and finally, yeah, utilizing the scores, we are finding the class finally. In fact, I am not digging down. So when you compare this random forest RF screen with the SOM screen, so the main difference is, yeah, so in fact, the accuracy of random forest is much better than self-organizing map. But when you see this, recall of SOM is much better than that of GPU RF screen, because we are classifying into we have another classification called an unclassified compound, yeah, which is reducing the false positives and false negatives, in fact, which may reduce the recall. Okay, so our second work also we published in a journal, Springer journal, yeah, called The Protein, yeah, the ligand based versus screening using self-organizing map. Yeah, so I'm concluding this session, after which my teammate will be explaining more about deep learning. Okay, so when I conclude, I'll tell you this: considering the large volume of data involved in ML-based ML-based ligand-based drug discovery, the proposed parallel methods can reduce running time. Yeah, the cost of installation, power consumption, and maintenance of a GPU-based systems are lower compared to other multi-core system. Why? Because when you compare an HPC system in which, yeah, so a cluster system in which we'll be having n number of, maybe nearly more than 10 nodes, the power consumption, etc., will be more there. Yeah, so GPU system is a better workaround. Yeah, so machine learning based virtual screening is a viable alternative for quickly screening large quantity of ligand data at a lower cost. Okay, so the ML-based technique requires the feature extraction as the first step. Yeah, so that's why the main difficulty of machine learning techniques are they need feature extraction. Yeah, so this feature extraction is a tedious task, and it takes a lot of time. Why? Because by using a third-party tool, etc., we are deriving features from it. So which is a difficult task. Yeah, that's why this machine learning techniques require feature extraction, which is appearing as a tedious task. So yeah, I'm showing one of the other remarks. By showing the other remarks of Alan Turing, I'm stopping this first session, and I'll pass it to control to my fellow teammate Pratimesh. Yeah. So Alan Turing told this also: I have such a stressful job that the only way I can get it out of my mind is by running hard. Yeah. So this AI, it's just like an ocean. Yeah. By putting more and more efforts, more and more fruits can be easily taken out. Okay. So yeah, so with this session, with this I'm stopping my first session. So maybe the participants can take 5 minutes time. Yeah, so Pratimesh will be setting his screen. Yeah, so Pratimesh, can you hear me?
Yes, sir.
Yeah. So you can share the screen and wait for 5 minutes. Maybe all those doubts and questions will be taking at the end.
Okay, sir. I hope my screen is visible.
Yes, sir, visible.
Hello, screen is visible, right?
Yes, sir, visible.
Okay.
It's visible, Pratimesh. You can give 5 minutes break.
Okay, sir.
All please stay online. We can have a break of 5 minutes.
Yeah, Pratimesh, you can start.
Okay, sir. I'll start. I hope my voice is clear
Yes, yes,
and
yes.
screen is visible.
Screen, I cannot see. Yeah, yeah.
Okay.
Make full screen, no? Yeah, continue.
Slides visible, right?
Yes.
Yeah. Okay. Yeah. Good evening, all. My name is Prathamesh Gaikwad, and today I will be explaining convolution neural networks and its applications. So, as Sir said in earlier presentation, feature extraction in drug discovery problem is a tedious task. Tedious task. So, how do we gonna solve this problem? So, the algorithm can process image as an input and can carry out this tedious task. To solve this problem, we need to build a structure capable of looking at an image, extracting relevant features from it, and then processing these features to complete the associated task. This structure fall under the domain known as a deep learning. So we will be seeing at the basics of the deep learning in this presentation, where in machine learning we manually need to extract the features in order to make the prediction. In deep learning, the AI model can itself take the tedious task of feature extraction as well as classification in order to give correct output. So, in basics of deep learning, the basic building block of deep learning is artificial neural. So, to mimic the human brain, neuroscientist and logician come up with the mathematical construct to mimic the way neurons of the brain behave. This construct is known by the name of artificial neuron. So, artificial neuron is a mimic of our brain neurons in artificial way. Artificial neural networks, just like how massive network of neurons create our human brain, a network of artificial neurons creates a artificial neural network. The image of artificial neural network is shown here. This network consists of the following layers: input layer, multiple hidden layers, and a output layer. So this is a basic structure of a artificial neural network. Artificial neuron. Artificial neuron is a mathematical construct mimicking real neurons. Each neuron takes a set of inputs, which are shown here as a x1, x2, x3, x4, and each input has a certain amount of importance, which are shown here as a w1, w2, w3, w4. In deep learning language, they are also called as weights. These inputs, along with their importance or weights, are combined to produce the output for the neuron. This circle can represent a neuron, and weights, inputs along with weights, make up the output from that neuron. This B is called as bias, and we will talk about it later in the presentation. Artificial neural network. So putting artificial neurons together, we can create an artificial neural network, or artificial, we can say it as an artificial brain. In artificial neural network, a set of neurons are organized in a layer. Each network consists of multiple layers of these neurons, and each neuron of a layer is connected with the each neuron of the adjacent layer. Hence, output of the all neurons in the layer are passed as an input to the next layer. As you can see in the image, each neuron is connected with all the neurons of its previous layer, so it can predict its output based on the input from all the previous neuron outputs. So this is how basic artificial neural network looks like. This is an example of how input flows through a typical neural network. So this is our input layer. The image of a handwritten digit 2 is passed on to the input layer. It propagates through the hidden layers and it produces output that the digit shown in the image is 2. So this is how the input flows through a neural network. Now, as you see seen in the previous slide, the input layer receives the data represented by numeric value. The hidden layers perform the most computation required by the network, and finally, the output layer predicts the output. So, in order to understand the neural network, we have to learn some basic we have to learn some basic terminologies of the deep learning. So some of them are shown here. First one is a learnable parameters. Learnable parameters are parameters that will be learned by the model during the training procedures, such as the weights and biases. Weights which were shown as a W in previous slide, and bias was represented as a B in previous slide. Those are called as a learnable parameters. Weights control the signal or strength of the connection between two neurons. In other words, a weight decides how much influence the input will have on the output. So, for example, in this neural network, if the input given by this neuron uh, has a has a more influence on the output, then the weights associated with this neuron, this and this, will have a high value, so it can influence the output more. So this is how uh, weights are given to the each connection, so they can produce the required output. And biases are constants, are they are an additional input to the next layer. Biases in the neural networks can be thought of as an analogous to the roll up constant in linear function, whereby the line is effectively transposed by the constant value. So bias, as you see in here, uh, to the multiplication of inputs and weights, we add one constant known as a bias, uh, just in case the model required some transpose in the graph to make correct prediction. So for that purpose, bias is used. Then each node is connected with each node from the next layer, and each connection has a particular weight, represented as a W. Weight can be seen as the impact that one node has on other node from the next layer. Another terminology is activation functions. In neural network, activation function defines if given node should be activated or not based on the weighted sum. Define the weighted sum value as Z. So here we have a A1, A2, AN as inputs, W1, W2, Wn as their weights. So in a single neuron, we will multiply inputs with their corresponding weights, add them, and add a bias with it, and we obtain a Z, which is called as a weighted sum. This weighted sum will be passed through a function G called as the activation function, which will give us a final output. So this is how a basic computation works in a single neuron of a neural network. There are various activation functions available, some of which most popular ones are sigmoid activation function, which produces output between 0 to 1 based on the input, which is our weighted sum, and ReLU activation function, which produces output 0 for a negative weighted sum value, and same output as input for the positive weighted sum value. So these are two popular of activation functions. There are various activation functions available. Then loss function. Neural network uses optimizing strategies like gradient descent to minimize the error in the algorithm. The way we actually compute this error is using loss function. It is used to quantify how good or bad the model is performing. These are divided into two categories: regression loss and classification loss. So in neural network, we have to update the weights in order to model predict output more accurately. So for that, we use gradient descent algorithm. For that, we need to give a model of feedback about how good or bad is performing. So to give that feedback, we use a loss function which computes the error error of the current output and gives a feedback to model about how it's performing. And now back propagation. Back propagation is the essence of neural net training. It is a practice of fine tuning the weights of a neural net based on the error rate, that is loss, which error which is obtained in the previous epoch. Epoch means iteration. Proper tuning of the weights ensure lower error rates, making the model reliable by increasing its generalization. So as I said, neural networks need to adjust their weight in order to predict the accurate output. So back propagation is the algorithm used for correcting the weights. So back propagation is the essence of neural network training, and proper tuning of the weights by use of back propagation reduces the error or makes our loss less, so the model can predict better and better. So a basic backpropagation works like this. The backpropagation algorithm in neural network computes the gradients of the loss function for a single weight by chain rule. So by the mean of computes the gradient function, basically a backpropagation algorithm computes how loss function is changing with respect to the weight, because weight is the parameter we gonna change in order to decrease our loss. So it computes the change in loss function with respect to change in weight. The weights initially at the start of the training, the weights are usually randomly selected. Then we calculate output for every neuron from input layer to the hidden layer to the output layer. Then we calculate the error in the outputs. Simple error is calculated as a actual output minus desired output. And then we travel back from output layer to the hidden layer to the input layer and adjust the weights such that during next iteration our error is decreased, and we will get less and less loss and better predictions. So the this is a typical back propagation, like how method works for a single neuron. I will be showing here. So first we will have a forward pass here. For the this orange circle is a single neuron, and it has a input in terms of two numbers, I1 and I2. They are zero point 0.5 and zero point 0.2, and they have their corresponding weights as a W1 and W2. And this here is a bias which is own weight. So first input will flow through the neuron in this is that is called as a forward pass. So here we will multiply inputs with their corresponding weight, and we'll get our weighted sum, and we will add bias with it also. So this represents weighted sum. Then we will pass this weighted sum through an activation function. This is another activation function shown here, and we will get our output. And let's say the correct or ground truth value for this input is a 0.01, but what we get is a 0.61774. So now we will calculate the error. There are various functions available for calculating error. We are using one of them, which is a square error. So we'll take a difference depend between target and output, square it and divide it by 2, and we will get our square error, which is a 0.184678. Now this whole process is forward propagation plus loss calculation. Now we will go now we have gotten our error, so we will back propagate. In back propagate, as I said, we will compute a gradient for loss function, like how loss function error is changing with respect to weight. So by chain rule, we get dou e total by dou w is equal to dou e total by dou out by dou net by dou w. So now this way obtained by chain rule, we can, by basic derivative rules, we can calculate the dou e total by dou out, which is a 0.607, dou out by dou net, which is 0.2361, and dou net by dou w1. And then by chain rule we will get dou e total by dou w1 value, which is how error is changing with respect to weight number 1. So by using this gradient or derivative value, we will update our weight number 1, uh, such that for during next iteration, the error we encounter will be lesser as compared to the previous iteration. So this is how a typical back propagation algorithm works. First we will forward propagate, then we will calculate the loss, and then we'll back propagate, obtain the gradient value, and we will update our weight such that it will produce a more accurate result on the next iteration. So how does this learn? So training ANN, artificial neural network, we pass the ANN the input. Initially, it produces a random output. We inform the model that the output is wrong by the use of by calculating loss and then back propagating. Then it goes back and tweaks the importance. Importance means weights, and it gives to every input, and this results in slightly better results during next iteration, and the model is again informed of its errors, and the processes continue till it reaches the desired performance level. So as the process which I shown here, forward pass, loss calculation, and then propagation, this will be carried on again and again until it predicts the good it predicts good results or less loss, and it reaches our desired performance level. So here is showing our showing how basically training works. Input will be given to and then model, it will predict output, then we will compare our output with the correct output out of ground truth, then we will get error. We will give feedback this error as will we give this error as a feedback to the model, then model will back propagate, change its weights, and uh, again produces new outputs, and this process will go on until it reaches the desired performance level. Now this is an example of learning process. Here inputs are flowing, first going forward propagating, predicting a result, then calculating loss, and it's back propagating to change the weights. So this is how ANN gets trained during ML training. Now, convolution neural networks. As we have seen the artificial neural networks, the artificial neural networks only in case of working with images, the standard artificial neural networks can only work with the small images, uh, because in ANNs we have to give input as a single dimension matrix. So if a image pixel size is very large, like 140 by 140 megapixel, or 280 by 256 by 256 megapixel, or maybe greater, then the size required of a artificial neural network will be too large and it will require too much computational power. So we use an alternative called convolution neural networks, which takes image as an input and it converts image into the smaller image by encoding each pixel with its neighboring context. So as you can see, this is how CNN works. Importance of CNNs. CNN allow us to process image faster and with lesser compute, and they have been used to create numerous models for various image related tasks. So for image related tasks, mainly CNNs are used because they provide good advantage, lesser compute power, and good results. Also, if we use ANNs for the image with image related tasks, we will lost our we will lose radial spatial information available in the image, and it will be hard for the model to train. So using CNNs for the images is a better approach. So importance of convolution neural networks. Why convolution neural networks are so much important? Convolution neural networks are distinguished from other neural networks by their superior performance with image, speech, and audio input signals. Along with images, it performs very well with speeches and audio input signals because in speech data types, in speech inputs also, the size of input is too large, similar to image. So it's better to use CNNs instead of ANNs. Using CNNs for deep learning is a popular due to the following main factors. CNNs eliminate the need for manual feature extraction. The features are learned directly by CNN. So in case of CNNs, we don't need to manually extract the features and then feed it to the model. The CNN can itself we can directly feed the image to the CNN. They can extract features on their own and make the prediction or required predictions. CNN produces highly accurate recognition region compared to other neural networks. CNN has a high accuracy in recognition task of images. CNN can be retrained for new recognition tasks, enabling you to build on pre-existing networks. So CNNs are highly suitable for transfer learning. This will reduce our time for training and as well as computational power. So this is how CNN convolution neural network was. We feed images to the CNN. It learns the features, first extract the features, then learns the features, and make the required prediction. Uh, this is a typical recognition task shown here. Now, how CNN works? Like other neural networks, CNNs are also have a input layer, output layer, and hidden layers similar to ANNs. But these layers have a different types. The three main types are convolutional layer, pooling layer, and fully connected layer. So this is image, this goes to the convolution CNNs and it will produce the output, and in between this there are different layers, convolution layers, pooling layers, and these are the fully connected layers. Now, convolution layer. The convolution layer is a core building block of a CNN, and it is where majority of computation occurs. It requires few components which are input data, a filter, and a feature map. The filter is also known as a feature extractor or kernel, which moves across the image, checking if a feature is present. This process is known as a convolution. The filter is then applied to an area of the image, and dot product is calculated between input pixels and the filter. As you can see in this video, this is our input image, this is our filter, and this is output of the convolutional layer. So for here for our input image we have this filter. This goes through each 9 by 9 in 9 by 9 submatrix, multiplies the data with its own weights and predicts the output in the output matrix. So this is how basically convolution layer works and predicts the output. Now the filter shifts stride by stride as you see in video, and also you can see here. This is filter, this is input image, and it's predicting it's giving output for next layer. The filter shifts stride by stride. Stride is a how many steps we are moving in each step in convolution. Here you can see the filter is taking two rows, skipping two rows at a time. So when starting it's here and then it's going here. So here the stride is 2. The filter shifts stride by stride, repeating the process until the kernel has swept across the entire image. So as you see here, it goes stride by stride and covers the entire image matrix in order to predict the output matrix. Zero padding is usually used when the filter do not fit to the input image. When the jumps taken by filter and the image length or width is not compatible, we use zero padding so that filter can move according to its generated rules. Also, zero padding helps us to give more focus on the uh, edge data, so edge data is not get lost, and we can use that data to for our prediction, because sometimes edge, the data present on the edge of the image is also important. So zero padding can help with that. Pooling layer, similar to convolution layer, pooling layer also ships filter across the entire input, but difference is that filter do not have any weights. Instead, it applies an aggression function to the receptive field. So similar pooling layer, in pooling layer also we have a one kernel which sweeps across the entire input, but that kernel don't have any weights. Instead, uh, let us suppose this is our input image matrix. Here we will use our kernel as a size of 2 by 2, so it will go to the first 2 by 2 submatrix. In case of maximum pooling layer, it will go to the 2 by 2 submatrix, will take the maximum data, maximum number available in that submatrix, and give predict it as output, then moves to the second submatrix, take the max, goes to produces the output. Similarly, it will sweep across the entire input. And there is another type called average pooling. Here also it will go to first submatrix, then average out the data points, and take their average as a output. Again go to the next submatrix, take average and take it as a output. So this is a pooling layer which differs from the convention that it don't have any weight. It takes a data point directly and just applies some max pooling or average pooling. The pooling layer helps to reduce complexity, improves efficiency, and limits the risk of overfitting, because they don't have any weights, but still they are reducing the image sizes. So they limit the risk of overfitting, and they improve efficiency and reduces complexity. Of fully connected layer. In fully connected layer, each node in the output layer connects directly to a node in the previous layer. As you can see in the image, each node in the next layer or output layer is connected to the all nodes of the previous layer, so that they can take data from all the nodes of the previous layer and predict their output. So this type of layer is called as a fully connected layer. While convolutions and pooling layers tend to use ReLU functions, ReLU activate function, the fully connected layers usually uses a softmax as an activation function to classify inputs appropriately, producing a probability from 0 to 1. Usually, convolution pooling has a ReLU as an activation function, not always, but mostly. While fully connected layer uses softmax as an activation function, it is another activation function which which takes inputs and produces the output in terms of probability in case of a multiple class problem. Now convolution structure of CNN. So for a model associated with the image task, a typical basic convolution model will look like this. It will have a convolution layers. Kernel means filter. It will have a convolution layers, max pooling layers, again convolution layers, max pooling convolution, so like that. And when the image size will get sufficiently reduced, then it will be fed into the fully connected layers, which will be having softmax or any another activation function at the last to predict the output. So basic convolution neural network model has a this type of structure. Bottom line, so researchers have discovered a way to build artificial intelligence into machines, such that machines can look at the raw data, learn from the features to extract, and how much these features contribute in producing the needed output. This technology can serve many purposes, especially in assisting the doctors by making their work easier. Next, we would like to present some of the areas in which we can apply these concepts. So as we see in the slides, how CNNs work. So researchers have discovered ways to build artificial intelligent machines which can uh, which can work on this theoretical concepts and do the tedious tasks like feature extraction and size reduction like that. So we will see some of the basic areas in which convolution neural networks are used. Classification. So classification is a technique to categorize our data into desired and distinct number of classes where we can assign label to each class. So in case of classification, in this is application of CNN, or you can say computer vision, in which uh, we can divide our data into the distinct number of classes and we can assign label to them, and the neural networks can do this tedious task of classifying them and labeling them. Classification can be applied to many different medical applications like cervical cancer type prediction, blood cancer prediction, breast cancer prediction, x-ray image classifications. Then this is how classification task looks like. So we'll be having various types of images, then it will be fed through the neural networks and it will predict the output about that image, like it is a cat or a dog. It will classify it into different classes. So this is classification task. Image segmentation, this is another application of computer vision or CNNs. Semantic image segmentation is the task of labeling each pixel of the image into predefined set of classes. So in image segmentation, we label each pixel of the image to a particular class. As you can see here in the image, this image when feed through a model class image segmentation model, it predicts as like this is a reference representation. So here you can see like the pixel representing person has a change its value. The the pixels representing the pixels of the walk path sidewalk are changed into another value. Even the small purse is changed into the another pixel value. So this is how image segmentation task is done. This is another example of image segmentation. You can see in this video how segmentation is done by the model. It will be assigned different colors to different objects, and it segmented each pixel to which it classified each pixel to which it's representing and colored that pixel according to the given colors. Now third is the object detection, which will be having more focus on. So object detection is locate the presence of objects within a bounding box and predict the type or class of the located output in an image. So output object detection is basically do two things. First, it locates the presence of object in the image, draws a bounding box around it, and then predicts the type or class of that object in the image. So here you can see it is identifying the various different body parts in the image. This is another object detection example. Here you can see in video it's identifying each and every object, also drawing box around it and giving it a label with certainty that this label is certain up to this percentage. So how object detection work? You can use variety of techniques to perform object detection. Popular deep learning based approaches using convolution neural networks CNNs such as a RCNN and YOLO automatically learns to detect objects within images. So in object detection, we mainly use convolution neural networks, and RCNN and YOLO. These are some of the well-known object detect pre-trained object detectors. Whether here you can see the image which is a detection or detecting a stop sign using a pre-trained RCNN model. It's detecting a stop sign with a 99% confidence. Whether you create a custom object detector or use a pre-trained one, you will need to decide what type of object detection network you want to use, a two-state network or a single-stage network. So object detection network has a two types, two-stage and a single-stage. Two-stage networks. The in two-stage RCNs use two-stage type of networks. So in two-stage networks, the initial stage of the two-stage network identifies the regional region proposals or subsets of the image that might contain an object. The second stage classifies the object within the region proposal. Two-stage networks can achieve very accurate object detection results. However, they are typically slower than the single-stage networks. So, as you can see in the image, the initial first stage identifies or identifies the image that might contain the its required object, and then it draws a box around it, and the second stage classifies or gives a label to that label to the object enclosed into the box. So this is a two-stage network works. RCNNs are typically used two CNN networks. Single stage networks. In single stage networks such as YOLO uses single stage network. The CNN produces network predictions for a regions across the entire image using anchor boxes, and the predictions are decoded to generate the final bonding boxes for the objects. Single stage networks can be much faster than two stage networks, but they may not reach the same level of accuracy, especially for scene containing small object. So here you can see a YOLO CNN, how YOLO CNN works. So in single stage networks, the CNN produces predictions for the across the entire images using anchor boxes and gives predictions, and then these predictions are decoded to generate the final bounding boxes for the object, compared to double stage two stage single networks. Single stage are much faster, but they lose some accuracy, especially in case the objects in the image shown are very small. So these were the two types of the object detection networks. So computer vision or CNNs has a mainly three applications: classification, detection, and segmentation. Identifying or labeling object is classification, detecting the object in the image is detection, and segmenting the images pixels represented object is image segmentation. So there are other applications of machine deep learning or machine learning also, recommendations. So machine learning algorithms can offer necessary medical information without need to actively search for it. So they can recommend the medical information. Clustering, also algorithms can group together similar medical cases to analyze the pattern and conduct the research in future. And text summarization. Machine learning algorithms can summarize the medical records and provide us the short, relevant information. So these are other applications of deep learning or machine learning, which we can use in medical sector. So this is all from my side. Thank you for listening me.
Yeah, thank you, Prathamesh. Yeah. So I think the participants can take another 5 minute
Yeah.
rest. Then, yeah. Surajit, yeah.
Yes, sir. So we can go for a break. Dear participants, take a 5 minutes break and join back at 8:24. Okay, thank you. Dear participants, please join. Teresa, please continue with the section. Yes, sir.
Yeah, hello. Yeah, so can you see my screen? I'll 1 second.
Yes, sir.
Can you see my screen? Yeah. So everyone joined or not?
Almost 26 participants, 25 participants are there.
Maybe 1 or 2 minutes more. We will wait and we will start.
Okay.
Because I'll be taking 25 minutes. Then
Okay, sir.
okay, I think we can start. Hello.
Sure, sir, sure.
Yeah. Okay. So yeah. So welcome to the session. Yeah, third session. The cervix type detection by a novel object detection algorithm. Yeah. So my teammate Prathamesh was talking about CNNs and its application, and object detection is a kind of a nice application where CNNs find its beautiful usage. Yeah. So I think you may be known about various object detectors like RCNN, fast RCNN, faster RCNN, mask RCNN, YOLO, etc. Main difficulty of these algorithms are they require anchor points, right? Yeah, so which makes the computing very tough. Okay, yeah. So before starting this work, our intention was to develop a method for early detection of cervical cancer. Okay, but I'm only going to talk about cervix type detection in this presentation. In fact, our works for cervical cancer detection, early detection of cervical cancer. In fact, we are developing a biomedical device for this. Yeah, in association with the Calicut Medical College. In fact, this work is in progress. Yeah, and moreover, we are applying for patent. So that's why such details I cannot disclose here. Yeah. So the cervix type detection, I'll be talking only about cervix type detection here. Yeah. So, as per WHO, cervical cancer is the fourth most occurring disease in women globally. In India, cervical cancer is third most common cancer and the second leading cause of death also. Yeah, it arises in cervix due to abnormal growth of the cervix cells. Yeah. So you may be aware, right? Cervix is an organ in woman. The lower portion of the uterus connecting the vagina is called the cervix. Cervical cancer is caused by uncontrolled and abnormal growth of cells inside the cervix. Cervical cancer is actually caused by human papilloma virus, also known as HPV, which usually incubates over a period of 1 to 2 decades. Okay. So early detection of cervical cancer is hard with simple observations as there are no specific symptoms in early stages. So yeah, the main the culprit of the cervical cancer is HPV, human papilloma virus. Yeah. So here you can see the anatomy of the cervix. Yeah, the organ cervix. Okay. Um, yeah. So in this, you can see a specific part here called SCG. Yeah. So the other name of SCG is called transformation zone. Yeah. So in fact, this cancer is affecting in this transformation zone. Yeah. So the cervical cancer has a long pre-invasive stage, taking 5 to 15 years to progress and finally reach malignancy. Cervical cancer can be prevented by early detection through the various screening methods. The commonly used methods of screenings are, Pap smear, so cytology-based method, which is called Pap smear, and LBC, the liquid-based cytology. They are cytology-based techniques. Yeah. Another technique is, other important technique is this visual inspection with biacetic acid, VIA. So visual inspection method like visual inspection after applying 5% of acetic acid and visually inspecting with even magnification. Yeah. So another method is HPV DNA detection methods. So yeah, also there is another equipment called colposcopy, using which you can say, so with high magnification, this experts can verify the cervix. So the high false rates for detection, all these techniques has high false rate due to the human error, inter-observer variability. Yeah. So the possible solution is to augment with machine's help. Yeah. So the cervical cancer, the major screening techniques available are on one. The first one is primary screening. Yeah, it's a mass screening in which a large gang of the woman will be called for this test, and this is mass. It's a mass test, right? Yeah. So in which the primary screening, so only the possibility of this cervical cancer will be identified. Later, then will be sent to the district headquarters, in which using colposcope, which is a costly equipment, this can be more viewed. Okay, so which is an expert verification. And third technique is actually by you taking biopsy. Yeah, this is the final command. In fact, the all doctors are believing in this. Yeah, taking the biopsy and sending for checking. Yeah, so when you see the WHO guidelines, you can see, do you have a screening program in place? Yeah, do you have enough resources to provide an HPV test? If you have enough setup, you can go for an HPV test. Otherwise, you can apply VIA, which is a low-cost technique, visual inspection with acetic acid. Yeah, this affected organ will be applied with acetic acid with 4% diluted. Yeah. So then after a few minutes, the experts can view the cervical area. So in the case of the cancer, thick acetoid lesions will be found, which is an indication of this the cancer. Okay. So the cytology tests are done by scraping out sample cells from the cervix area to check for cellular to check for cellular changes using a Pap smear or LBC test. VIA is alternatively used for screening by applying 5% strength acetic acid and visually inspecting the cervix to detect changes. So where the abnormal areas appear thick acetoid, So this white will appear in this area. Yeah. So this cervix has actually two portions: ectocervix and endocervix. Yeah, ectocervix is visible through the vaginal orifice using a speculum. Yeah, it's a round-shaped one. Yeah, and opening at the center of ectocervix leads to a canal called the endocervical canal connecting the uterus. At birth, the ectocervix is lined by squamous epithelium and endocervix by the columnar epithelium. At certain age, the columnar epithelium will be replaced by squamous epithelium inside the cervix, starting at the original squamous columnar junction, SCJ. That's what I was talking about, this SCJ junction. Yeah. So this SCJ junction will be affected with cervical cancer. Yeah. The area of changing cells between new SCJ and old SCJ, this section is called transformation zone, which contains immature cells which may get infected by HPV, human papillomavirus. SCJ is an important landmark in VIA, visual inspection with acetic acid, and colposcopic test, since most of the atypia lies near this in this transformation zone, affects this cancer. Yeah, depending on the location of the transformation zone, we can categorize the transformation zone and cervix into 3 types. Yeah, and there you can see these 3 types as this. Yeah, so type 1, type 2, and type 3. Yeah, so in type 1 cervix, the transformation zone is fully visible from outside. It is completely ectocervical and does not contain an endocervix component. That's what is shown here. Yeah, so it's fully ectovertical, that is, which is visible that's outside. Yeah, so it's fully visible. Okay, in type 2 cervix, the transformation zone is fully visible, has both endocervical component and ectocervical component. That's what it's seen here. Fully visible, it has both ectocervical and endocervical. Yeah, so and in type 3, the transformation zone is not fully visible. It has an endocervical component and also an ectocervical component that varies in size. That's why you can, so it's digging inside this canal. Okay, so it has endocervical component mainly. Yeah, so it is this details are not visible. So yeah, so knowing the cervix type is actually very important in identifying the treatment specific to the geometry of the cervix. If the cervical cancer is identified, to give the treatment, right? Yeah, so identifying the cervix type is also important. Yeah, so whether it is type 1 or type 2 or type 3, that's why we have chosen this project. Yeah, so you can see a general pipeline in which computational techniques can be applied for finding, for classifying this. Yeah, the input image, pre-processing, feature extraction. But if you have CNN, this is not required, and classification. Yeah, so yeah, this is the same pipeline for pap smear slides, a slide image. If you have a slide image, you can pre-process, then feature extraction, or directly applying CNN and classifying it. Okay, so our problem statement is this. In fact, we wanted to classify the cervix into 3 types. So yeah, so the problem of this the data sets available, the given for this experimentation, the main difficulty we found was when you see this, the actual cervical area is small and it is not zero-centered. Yeah, so that's why to find a region of interest efficiently, our actual problem statement stands here like this: to find region of interest efficiently and classify a colposcopic image of cervix into 3 types based on a transformation zone, whatever I showed earlier. Yeah, so the basic problem of these data sets are they are of large dimension, and cervixes are, these images are not zero-centered. Yeah, so size of the image in the data set was also large. So finding an accurate ROI, region of interest, will actually improve the training of the model. Yeah, so these are the data sets which was available for our work. Yeah, so we got this data set from Kaggle the mobile ODT competition. Yeah, so as you can see here, we were having 3 cervical types images. Yeah, we call it as cervigrams. Okay, the initial data set, they released 2 data sets. One is initial data set, other one is additional data set. Yeah, in the initial data set, we can see only few pictures, but they are of high quality. In additional data sets, these images were of bad quality. Yeah, so and in fact, after these competitions, some of the researchers were annotated this actual cervical area. Yeah, so they have drawn the bounding box, and these annotations of 1,000 images were available. Yeah, so as I told you, for the data preparation, these 2 things were difficult for us. The size of the image, they were of 2,500 into 3,500 pixel level. So, but to apply any CNN or something, we need less than 512 or 300 into 300 in that level. So reducing image size was one difficulty. Other one was more, when you see most of the figure, they are not zero-centered. These are BGR images. So they are not zero-centered. Yeah, so these 2 are the major difficulty we faced. Okay, So that's why we thought of going with a two-stage architecture. My friend Prathamesh was talking about both one-stage and two-stage object detection architectures. Yeah. So the main advantage of two-stage architecture is in one stage we can cut the ROI, region of interest, and utilizing this you can go for a classification. Yeah. So even though it is bit slow, I mean, this technique has two stages. Yeah, this gives more accuracy. Yeah. So we also incorporated a technique called self-supervision, yeah, which I'll be explaining in the coming slides. Yeah, and we have derived a new object detection detector here called efficient sender net. Okay, so efficient sender net. Okay, so our work. I mean, this describes the workflow. Yeah, data collection and cleaning is the first step. We have applied manual cleaning because some of the images available in the data set was even not of cervix also. Yeah, and since it was an endoscopic images, the even pictures of finger and hand was also visible. Yeah, so the cleaning was our first step. Second step was deriving an object detector which will detect the cervical area, the region of interest. After detecting the region of interest, we will be cropping it and passing it to the classifier. Yeah, so that's how our system works. Okay. So, so it's a two-stage architecture in which first stage will be cutting the ROI, and second stage will classify the image. Okay. Yeah. So for developing this efficient sender net, we have utilized efficient net as a feature extractor. Efficient net is a it can be seen as a group of CNN models, and it is more efficient than most of its predecessors. Yeah. So there are 8 models starting from B0 to B7, and you can see the trade-offs. Okay, the number of parameters, accuracy, and the computational budget is changing from B0 to B7 as it is seen in the table. Yeah. Yeah, since EfficientNet B4 offers a decent trade-off between flops and accuracy, it is taken as a backbone of for both object detector and classifier. Yeah. So to develop an object detector, we require the feature extractor. So we have chosen EfficientNet B4 as the backbone. Yeah. So we have added by FPN layer. Yeah. So these layers are called bidirectional feature pyramid network. So they show. This figure shows that they can be used as an additional 4 layers of BiFPN layers are added for which will improve the multi-scale feature fusion in the in an efficient manner. These highly connected BiFPN blocks fuse features from multiple levels of network, increasing the data flow for individual units. Hence, they increase the overall performance. Yeah. So we have chosen efficient internet before as the feature extractor. When you add BiFPN, which will increase the data flow and which will finally increase the overall performance of this detector. Yeah. So yeah, so that's what it is seen here. So to develop an architecture, to develop an efficient object detection architecture, yeah, as I told you, we have used an BiFPN blockouts, which will take 5 channels, which is then sender pool. Yeah, this sender map is another idea which uses heat map techniques, which will help us to identify to fix the zero centering issue of the input image. Yeah. So by mixing BiFPN details of efficient net plus BiFPN plus sender net details, this efficient sender net architecture is derived here. Okay, so it basically uses 3 loss function. Yeah, heat map or classification loss, and then size loss and offset loss. Those details are given here. So as it is seen in this picture, this heat map which will identify this cervix mouth, and utilizing which zero centering issues of this image is removed here. Okay. Yeah. So I told you to improve. As you can see here, the data set was comprising of only less number of data sets. Yeah. So a better deep learning technique, a good model, deep learning model will require actually a lot of image sets to produce a better output, right? Yeah. As a solution to this problem, we propose a self-supervision boosted pre-trained network for the ROI proposal network, which is trained only on 1,000 images, which was annotated by another researcher, right? As I told you in the beginning. Yeah. So to utilize the limited data set available to get the best performance, we incorporated the self-supervision technique with this ROI cutter. Yeah. Yeah, so we used a special technique called image in painting. So image in painting is a conservation process where damaged or missing parts of the images are topped up to form a complete image. For the cervix image detection, the foreground area to be segmented are called as the region of interest or ROIs. Image in painting improves the determination by choosing the homogeneous region. Yeah. So now the network is made to learn the anatomical meaning by masking such regions in the cervicograms. This masking forces the model to properly interpolate the structures around the missing area. Yeah. So the considerable amount of increment in accuracy was observed by applying this image in painting, which is acting as a self-supervision technique in our cervix detection. Yeah. So in this self-supervision, the loss function used was L2 loss, whose the equation is shown here. Yeah. So in fact, this is our total prediction pipeline. Yeah. So as I told you, the input image, which will be passed through the efficient center net, which uses efficient net B4 architecture as the feature extractor plus YFPN layers, and which will be finally passed to the CenterNet idea of heat map, which will identify the cervical the area, the cervix area region, which will be cropped and will be this cropped image will be passed to the classifier. This is the total pipeline, yeah, which is a two-stage architecture in which first stage we will be identifying the ROI, means we will be cropping the ROI region of interest, and second stage we will be classifying it. Okay, so we have derived this. So we have derived the efficient center depth, and we just compared the accuracy of this with faster RCNN, precision, all performance of this efficient center depth with faster RCNN. For this, we have identified other data set, which is a skin data set, ISIC data set. So in which we applied both fast RCN and efficient center depth, and we have got a better mean IOU for our efficient center depth. We also compared our efficient center depth object detector with other object detectors which are commonly available. You all know CenterNet, fast RCN, and etc. So on this cervical data, so we found that our efficient center depth, which only takes 13.7 million of parameters, so which is very lesser in this table, and but it produces this IOU, intersection over union, which is a better IOU, 0.632. Okay. Yeah. So for implementing this, we have utilized these details. The framework used was TensorFlow, and the server machine used this actually NVIDIA. A server which has an NVIDIA Tesla V100 GPU card, which has 7,000 CUDA cores available in it. So this was having 32 GB graphics RAM. Yeah. So this infrastructure was available at Central Computer Center and NIT Calicut. Yeah. The source code of the total work is available in this link. Yeah. So now to compare the model performance, yeah, you can see we have created this table gives the comparison. Yeah. So incrementally we build this efficient center depth. Initially, efficient net B4 without ROI cropping was tried, which gave us only 58% accuracy. Then efficient net B4 plus ROI proposal network, which gave 71%. But then we introduced self-supervision technique, which gave 78. But then finally we introduced technique called ensembling. Yeah, so ensembling is a common technique in which it's a powerful technique in statistical modeling of data. We get the best accuracy by using multiple models learned in different samples of data. Yeah, we finally got 87% of accuracy when we applied ensemble version. Yeah, so this is the model loss and the accuracy and loss curves obtained. Yeah, and the confusion matrix obtained is also seen here. Yeah, so this gives an insight of how the model is performing in each class. The model has classified the images into right classes of 174 images of 200 images. Yeah, actually, our test set comprised of 200 images, yeah, out of which 174 images were rightly classified. The model misclassified actually type 1 or type 3, as our type 2 is highly available. Yeah, this is due to the imbalanced nature of data set. Our data set was having more number of type 2. So this type 2 has a relatively higher number of data. Because of this type 2 data sets, we were having more in number, due to which algorithm is bit biased toward type 2. Yeah, so these are the performance evaluation obtained. Yeah, finally we published this work in a Wiley journal. Yeah, so in fact this is available in Google. Yeah, so let me conclude this work. The cervical cancer is the fourth frequently occurring cancer. So determining cervix type will always help the doctors to prescribe the proper medicine for cervical cancer case. Yeah, so whether it is type 1 or type 2, type 3, yeah, because as I showed you earlier, some of them which has ectovertebral cervical and endocervical, sometimes it will be inside the canal. So accordingly, they'll have to prescribe the medicine for this. So in fact, we have developed a deep learning based pipeline to detect the cervix type. So we developed a two-stage architecture in which first stage will cut the region of interest ROI. We will identify the ROI and crop it, and which will be passed to a second stage, which will classify it as either type 1, type 2, or type 3. So yeah, so this the complete pipeline, it can be used for identifying the cervix type. These are the references used. Yeah, so that's about this case study. So yeah, we are in fact developing a biomedical device for early detecting the cervical cancer. So in that biomedical device, we are utilizing this ROI cutter, in fact. So this ROI cutter, whatever we developed as part of this work, is directly utilized in there. And in fact, in this work, we were having only type 1, type 2, type 3 data sets, right? So in fact, the positive and negative cancerous cases we collected from Calicut Medical College, utilizing which we are in fact detecting the cervical cancer from the cervigrams. Okay. So our other pipeline is also ready, and the hardware device, which has a computing device and a camera, is also ready. And in fact, we are embedding this AI software into that device, and we have given this for patenting also. So because of this patenting issues, the other side of this project I cannot explain more. In fact, the actual the design of that biomedical device is actually more attractive, but I cannot do it here. Okay, so with that, I'm stopping my talk here. So if you have any questions, you can ask me.
Dear participants, if you have any questions, please share.
Good evening, Dr. Jairaj.
Yeah. Hello.
Dr. Jairaj, you have told us of the GPU-based virtual screening technique, right?
Yes,
So, in
initially.
that, what made you come to the random forest algorithm?
Yeah. So why? Because it has. So we as an initial experiment, we tried SVM and random forest also. So this, because of what we identified was it has a bagging technique, right? So every time when we take, because for this node split, we are taking M features from out of capital M. So every time in bagging technique, we are taking a new set. So which is actually giving more power to random forest for classifying it. So we actually did an initial experimentation with because with third party Vecca tool, etc. We have done it, and we found that random forest is giving more results in this.
So, you had a clear comparison between the different techniques, right? Maybe
Yeah,
SVM,
initially
KNRF,
we made a pilot study. Yeah.
All right, sir. And one more thing, sir, in the second, the cervix cancer detection that you have told,
Yeah.
Initially, thereafter, once you take the ROI, you are giving it to a CNN, right?
Yeah, yeah.
So,
It's again same efficient net before architecture.
okay, so will that be a costly affair, or for the implementation, thinking of the implementation side, will that be a costly affair?
No, why? Because I told you, efficient net before
Uh-huh.
it uses less number of parameters, and
Okay.
it's a lightweight architecture. That's why even we are porting it into a Raspberry Pi and Jetson architecture.
Okay.
Jetson Nano and a Raspberry Pi, these embedded computing boards, they can easily they can afford this easily.
Okay, right. So anyway, this has to be a
The,
less costly matter, right? So people will go, they'll go and check it, right? So if it's too costly, it would really affect, right?
costly in the sense.
Costly means, if you are going to have a check on this cervix cancer,
Uh-huh.
right? So yeah, this is only one thing, right? That is there. Okay, okay.
Yeah, we in fact we are trying VAA, visual inspection with acetic acid. Right?
No,
Yeah.
no,
Okay.
the detection technique is only present at a point, right? At one place, maybe in a district, isn't it?
Yeah, yeah. Initially, whether if when the image is captured, this ROI will be cut and will be
Okay.
passed.
All right. Okay. Okay. Thank you, sir.
Yeah.
Okay, thank you. Now I invite Professor Sujit for presenting a virtual memento to their answer. Producer?
Hi all, we all have a wonderful session. Finally, as an appreciation to Dr. Jayaraj sir for his valuable session he has shared with us today, I would like to offer him a small virtual memento on behalf of you all, as well as the Department of Electronics and Communication Engineering.
Yeah. Thank you, Surajit.
Sir, 1 minute to share. I am sharing, sir. 1 minute. Thank you, sir. Thank you for your valuable information.
Yeah, yeah. Thank you, thank you. Anyway, maybe next time we can make it offline. So online is actually a bit difficult for me also. Why? Because yeah, this is only talking to computers, right? If there is a mob in front of us, then more creativity will come automatically. Yeah. So maybe next time we can make it offline.
Sure, sir. Sure, sure.
Yeah. Bye. So I can leave, right?
Sir, thanks. Thanks, session is done.
Yeah.
Okay, now I invite Professor Nidhi Habib, Muslier College of Engineering, Pathanamthitta, for delivering the vote of thanks.
Good evening, everyone. Am I audible?
Yes, ma'am.
Good evening, everyone. I take this opportunity to thank Dr. Jayaraj PB for his wonderful session on the topic application of machine learning in drug discovery, and also the second session, which he showed a case study on object detection algorithm. So it was a really informative session. You gave a deep insight into each and every topics. So even I felt second session is a bit more interesting, and you showed how object detection algorithm can be applied in early cervical cancer detection and all. So all the best for your teams for developing such an equipment for early detection, early cancer detection, especially for women. So it will be definitely a milestone in medical field. And I also extend my sincere thanks to Mr. Prathamesh, who had given us a wonderful session about CNN and its applications. So once again, I thank all the organizers for giving us such an informative session. Thank you all. Thank you, sir.
Thank you.
Okay, the session is over. Tomorrow we can have the session at 6:50 p.m. Indian values ethos. That will be the topic. Thank you.